All right, engineering physics class. Hello. Can you hear me back there?
Oh yes, I can hear you.
Wow. Great. So, hello. Can you hear me back there? How am I doing that? I was talking without even talking. So. Dr. Wisbey's Physics Hour, there it is. It's a good show, you should watch it. Or just come to class and see it live. So, live, Dr. Wisbey's Physics Hour. So, I didn't get a lot of liquid nitrogen last time. And I felt very bad about that because I really like liquid nitrogen. I like things that are cold. Right now in my refrigerator, I've been trying to measure a qubit. It's running a scan right now, but and it's very cold. It's at 40 millikelvin. So that's actually much colder than liquid nitrogen. Liquid nitrogen is very hot compared to my refrigerator. It's at 77 Kelvin, which is actually very hot. And so today, let's see. I'm going to show you some liquid nitrogen, and we're also going to do an experiment with electronics because, oh look, there I am. Hi, Dr. Wisbey. Takes a second to show up, but there it is. So I can see myself, and I'm going to try not to destroy anything. I'm going to pour a little someone left their mug here. It's a nice mug. It'll work great with liquid nitrogen. Do you want to get your iPad? Yeah, I would get it. Don't put electronics up here.
Don't put electronics for you.
Yeah, now my computer's there. I don't think I'll destroy it, but it's okay. This isn't really that dangerous. Okay, so I'm going to pour some liquid nitrogen into my coffee mug here. Whoa. Okay. So we have some that's cold. So I have some liquid nitrogen in here. Then this nice coffee mug. This is hopefully it's a very nice mug. It's insulated, which is very good. Okay. And I'm going to pour some liquid nitrogen into the Pepsi bottle here. Okay. It's very cold. I'll just pour it all in there. Now I don't know if you can see it, but there's little droplets of liquid nitrogen rolling around the floor on the table, and I'll probably dump some out later. Now this is so what I have. I poked a hole in the side of this, and I'm going to put the lid on. Okay, I'm going to screw this lid on. Now I don't know if you can see this. So there's a little spout here, and it's blowing. You can see it blowing steam out of the side, basically. So, I don't know if you can see it or not, but I don't want to break it because, well, the liquid nitrogen will get out. But I also brought some ice. Okay. I have a container here full of ice. And what do you think is going to happen if well, let's put it in this container here. This is nice. There's still a little bit left in there. What do you think is going to happen to the liquid nitrogen when I put ice in this container? So, well, is ice hotter than liquid nitrogen? Yeah. So if you put water ice into liquid nitrogen, it's going to be very hot. So if there's any left in there, then it's going to basically, it's so hot that it's going to start boiling the liquid nitrogen. So you can actually take ice and boil liquid nitrogen with it, because liquid nitrogen is much colder than ice. I'll put a little bit more in there. So now what's happening is, as the ice gets colder, then the ice will actually drop in temperature and it will get to liquid nitrogen temperature. But so this is full of, it's full of liquid nitrogen now, and I'm going to put some more ice in it. So let's watch. So it's like and it's really starting to boil now. It's really hot, and so the liquid nitrogen is actually boiling, and there's lots of steam coming off of it. This would be like if you took a hot rock that was maybe several thousand degrees, and then you put it into a pot of water. So it would start boiling the water, but this is just much colder. So now the ice is cooled down. It's very, very cold ice now, so it's much colder than it was. And so we've sort of reached thermal equilibrium here. Now, what do you think would happen if I plug this hole here? Would that be bad? What would happen? Well, it would probably explode. If you have a liquid nitrogen container like this one, I have the lid on very loosely, but if you had a tightly attached lid with no valves, then the container would explode. And so sometimes when safety valves on liquid nitrogen freeze, you can have an explosion. And one time I took my wife on a date before we were married, and we went out in the country. But don't worry, we were with other physicists, and somebody had liquid nitrogen, and so they put liquid nitrogen into a pop bottle and then put water inside of it, and they sealed the lid really quickly and then threw it. And so what do you think happened? It would explode in the air, and it was extremely dangerous. I had no knowledge that he was going to do that, but my wife-to-be was not very happy with me. So I'll do one more. Oh, actually, so I do have another experiment with the liquid nitrogen. So we're going to start talking about resistors pretty soon. We haven't talked about them yet. Okay. But does anybody know what a resistor actually does? So in electronics, we have these things called resistors. Right? This provides something called resistance, and it's like if the electrons or the current is flowing through the resistor, this makes it more difficult. Right? Now, as electricity flows through the resistor, right, there are actually particles that flow through the wires, okay? And as they're going through, now, what happens to electronics as you have them on for a while, to the temperature? They start to heat up a little bit, okay? Just like in your toaster, this is the best example. When you run current in your toaster, you put your toast down, you push on the button, it starts to run current through the heating element. The heating element's getting hotter, and it's taking the electricity and is converting it into thermal energy. Well, it's taking the energy from the electricity, okay? So all of the electrons still make it through the toaster. None of them stay in the toaster. So when I say I'm taking electricity and making thermal energy, well, all the electrons are still there because charge is conserved, okay? but your toaster won't work unless the electrons can flow completely through it. So that's called completing the circuit. Okay? Now, inside of the toaster, the thing that gets hot, I want to show it to you. So I need about 30 volunteers. So, okay, everybody who wants to come down here and stand over there. Huh? No. Well, no. Okay. So we need more volunteers. This isn't enough.
Gabby, come on down.
Okay. This is getting better. It's getting better. So stand kind of in a clump close together. Okay. And let's see. Joel, I want you to be the electron. Okay. So I want you to and make a little bit of space between you guys. Okay. Now, Joel, I want you and guys make a clump that's kind of lined up this way. Okay. So start right here, and then make 2 rows that go this way. Move a little bit this way, farther. Okay. So like this. Okay. More. Go more. Forward. Okay. So Joel, now what I want you to do is I want you to try and walk between those 2 rows, Joel. Okay. No, start over there actually. Okay. So start over there. Okay. So let's pretend that Joel is an electron, and this empty space here, this is the conductor. So this is the copper wire. Okay. So Joel, head towards. This is our resistor over here. Okay. So Joel, I want you to walk between these two lines here. Okay. Actually go between them.
Try to stop.
Wow, this is very high resistance. So let him go through a little bit. Make a little bit of space. Okay. So what's happening here to the electrons as they go into the resistor? We have to let them through eventually. The electrons can get through. Okay. So it's very difficult for the electrons to get through. Okay, so now I want you guys to make a little more space here. Okay. And, okay, Joel, start over here again. And, okay, guys, now I want you guys are really hot. You're in the resistor, so you're like vibrating. So kind of move around. Move. You can walk around back and forth. You know, move about a foot. Awesome. Okay, Joel, now try and get through there. Try and get through the resistor now, Joel. So what's happening to Joel?
He's getting bumped around.
He's getting bumped around. And is he going in a straight line?
No.
No, he's not going in a straight line. Okay, now I want you guys to spread out like you were, okay? And I want you to move, not move at all, really slowly. Okay, now Joel, try and get through there. You guys can barely move. Okay, so this is like if the resistor is cold. And now what's happening to Joel as the resistor cools down?
It goes in easily.
It's a lot easier. So the resistance is much lower. Okay, now let's do one more. Okay, guys, get close together, make a line. Okay. Now, Joel, as you go through, I want you guys to oh wait, but you have to hold somebody's hand. Who wants to hold Joel's hand and walk through? All right. So hold hands, and as they walk through, I want you guys to spread out and let them pass, and then go back around them, like a wave. So as they approach, make a path. Okay, let them go through. Start walking, and then close behind them. But don't actually touch them at all. You can't touch them. Okay. So, okay. Now what was this? Okay, you can now go sit down now. You don't have to hold hands anymore. Thank you. So what was the last example? It's a physics charade. So you guys have to guess what it is. You have to figure it out. That's how charades work. So what was the last one? Oh, I froze my Pepsi. Oh. What? What was the last one? Well,
It's almost a guy.
was what?
It's like a guy
No, it's something in electronics.
Oh, okay. Think about
Yeah. Did that one? Did the last one have any resistance? Didn't know. It didn't have any resistance. Yeah, it's a superconductor. So it's a superconductor. Okay. Now, why did he have to hold hands? Because it took two electrons, and why did they have to hold hands with each other?
They have to be linked.
They have to be linked together by something called the phonon, or a vibration. So a phonon is actually a wave that travels through the crystal lattice, and when the electrons go through the superconductor, it's almost like the crystal lattice is moving out of its way, and the electron can go just pass through it. Okay, so now I actually brought a resistor with me, and it's a pretty high resistor. So I have an ohm meter here. I can measure the resistance of things, right? And so I'm going to hook up two wires, one into common or ground, and then the other one into positive or red or voltage, okay? And I'm going to hook it up to my resistor here, okay? And this says that the resistance is 26 kiloohms. So it's a little bit big. It's kind of a big resistor, okay? So this is 26 kiloohms, okay? I'll put it right there so you can see it. So it'll be on the screen. I'm going to get some more liquid nitrogen, and I'm going to pour it into this container. So there's my resistance. Okay. Now we're going to fill up our cup again. Whoa, too much. Oh, overflow. Yeah. So, okay. That's okay. So this thing's very full of liquid nitrogen. It's almost at the top. Okay. So you can see my resistor here. And I'm going to take my resistor. Hey, oh. Don't worry. It's okay. I'm going to bring my liquid nitrogen over here. Don't drink liquid nitrogen, very bad. Okay. And I'm going to put it inside of there. Oh. Okay, so let's see if it's working. What did it start as? It could have cracked. I don't know. I've never done this before. I actually don't know what would happen. So apparently the resistance goes up when you put in liquid nitrogen. So why would the resistance go up? That's really strange. No, because if I take it out, so as I'm grabbing it, it's going up. It's definitely going up. So I'll just leave it in the liquid nitrogen. And when I put it in there, it actually goes up, which is strange, which makes me think that this resistor is actually made out of silicon. Does anybody know what happens to silicon when you get it cold? No. Well, actually, when you get silicon cold, there are actually less charge carriers available. And so it would seem that the resistance actually goes up. But like I said, I've never actually done this before, so now I'm going to have to go figure out why it didn't work the way I thought it would. So I'll do another experiment because I think my resistor is actually made out of silicon, and so now we have some weird sort of semiconducting properties. So now what I'll do is we'll just hook up a wire. Well, it's cold. So my dead rabbit friend Marvin, his name was Marvin. Okay, so let's look at of just this wire. Our resistance is 7 ohms, okay? And let's stick our wire in here. Oh, it froze. Okay, so as I put the wire in there, the resistance actually went up. So it went up from 0.6 to 1.2, okay? So if I take it out, I heat it up again, it's kind of cold. Oh, it's really frozen. Okay, well, let me heat this up again. Okay, so now it's 0.1, and I'm going to stick it in here again. We'll see if it changes. Maybe it won't. That's okay. Sometimes it doesn't work. All right. Oh, I think it's not working. So it went to what this thing says is 0, and I'll take it out and we'll see if it changes over time. Okay, so charge, okay, and we were discussing fundamental particles. And we talked about the electron as being a fundamental particle, just like what a proton and a neutron are also composed of. Okay, so protons and neutrons are composed of other particles. Those particles are called leptons. It's a type of particle. And the particles that it is composed of are fundamental particles, and those are called quarks. Okay. And so we can see here in the proton, the proton is composed of 2 up quarks and 1 down quark. So up quarks have a fractional electron charge of positive 2/3 e. So we have 2 of those. And then a down quark has an electric charge of minus 1/3 e. Okay? So if you add those together, that equals 1. 2/3 plus 2/3 minus 1/3, it gives you 1. So the proton has a positive charge of 1 e. Right? Now, the neutron, it's composed of 2 down quarks and 1 up quark. So if we add the total electric charge of those fundamental particles of quark, so we have 2 down quarks, so minus 1/3 plus minus 1/3 e, plus 2/3 e for the up quark, that gives us a total charge of 0 for the neutron. So this is my neutron here and my proton. And those are the quarks are fundamental particles. Protons and neutrons are not. So we have not actually ever observed quarks directly, okay, because they're very difficult to measure. You can't really make an experiment, at least no one has thought of, that can really measure those. We know that these are not fundamental particles, and quarks explain a lot of things in physics, and that's why we know that they're real. We can use them to model things, and so there's good evidence that they're real. Okay, and the neutron, yeah, so the neutron is also composed of quarks. Okay, so let's talk about net charge. Okay, so let's suppose we want to create a net positive charge of 10 microcoulombs on a block of copper metal, and we want to do that by removing electrons. Okay. Now we know that copper has equal number of protons and electrons normally, and so the idea is if we want to give it a charge, a positive charge of 10 microcoulombs, we're going to need to take away some of those electrons. So how many electrons do we need to remove from the copper to get this charge? Right? So we know the atomic weight of copper, it's 63.55 grams per mole. Okay? So we can calculate the number of atoms in a 2 kilogram block of copper. Okay? So we take the mass of our copper block, 2 kilograms, we multiply that by Avogadro's number. That tells us how many atoms there are per mole. And then we take our atomic weight in kilograms per mole, and we multiply that all together, and then we get the number of atoms as 1.89 times 10 to the 25. Okay? But we need to know how many, what fraction of this, and that's also, we need to know, so how many electrons does each copper atom have? Well, we know that from the periodic table, the atomic number of copper is 29. Okay? So there are 29 electrons per atom. Okay? So if we multiply 29 by the total number of atoms, that's going to give us the total number of electrons in the block of copper. Okay? So now we can find the charge, the total charge of all the electrons. Okay? So we have Q equals E, the charge of the electron, times the number of electrons. Okay? That's going to give us the charge of this block. Okay? Then the number of electrons in 10 microcoulombs is thus, so we have 10 microcoulombs. We divide the charge that we want, okay, by the charge of one electron. And this is going to tell us how many electrons we need to remove to get that charge. Okay? So we take the charge that we want, 10 microcoulombs, so 10 times 10 to the minus 6 coulombs, divide by the charge of an electron, 1.602 times 10 to the negative 19 coulombs. This will tell us the number of electrons that we need to remove. But the original question was, what percentage of electrons do we need to remove? Okay? So how many of those, what percentage of the total electrons do we need to take away? Okay? So then, I'll use my magic wand, which makes me feel like Harry Potter. And so here, can't reach up there, but we take the number of electrons that we need to produce that charge, and we divide it by the total number of electrons in our block of copper, and multiply it by 100 to get a percent. And so, just by removing 1.14 times 10 to the minus 11%, that would give us a charge of 2 coulombs on our block. Okay, so we just would need to remove a very, very small fraction of the total number of electrons. Okay, so for the most part, we're going to start by talking about two main types of materials. One is an insulator and one is a conductor. So those are kind of the two most basic forms of materials. Okay, so an insulator does not conduct electricity. So my plastic rod here is an example of an insulator. It's plastic. It's not going to conduct electricity if I touch something at a high voltage. So if I touch my Van de Graaff generator here, if it was on, then it would not shock me. And also the plastic here is not conducting as well. Okay? So this cat fur is not conducting. Wood generally is not conductive unless you get it wet. Water is a conductor, so just like metal. Actually, water with ions in it, so if there's something in it. So your tap water is conductive because it has salts and minerals in it. If you have pure water that has all the impurities removed, it's called deionized water. And if it's really good deionized water, it is not conductive. Okay? So conducting electricity means that electrons can move through it. There's a transport of electrons. Okay? So as the electrons are moving through this material, right? If we imagine the atoms inside of my piece of metal here, right? The electrons will pass from one atom to another. Okay? So it's like in a metal, the outermost electron, the one that's most loosely bound to the nucleus, will basically give its electron to its nearest neighbor, but then since it has a vacancy, it will take one from the other neighbor next to it. Okay? So as the electrons are moving through the material, and actually in a metal, okay, the outermost electron is very, very loosely bound to the atoms, and so they're kind of free to move around in the metal. And they call this the electron gas. Okay? And so these conduction electrons can move around inside of the metal. Okay? Now, if you have a resistor, okay, as they're moving through this, right, if it's a resistor, and even in a metal, they, just like we saw with Joel, they undergo collisions. So the electrons are going through the metal or a resistor, and they can undergo collisions, which gives us resistance. Okay. Now, things that conduct electricity well are called conductors. Each metal has a different conductance. Copper is one of the best conductors out there. It's very cheap. Steel is not as good as copper, but each metal has its own resistance. Okay? Electrons can move freely. Some of the electrons, not all of them, the ones that are close to the core, we call those the core electrons, and those don't participate in the conduction of electricity. It's only the outermost loosely bound electrons that do. The core electrons in the atom are held very tightly, and they can't move away. Okay? So they're stuck there. So electrons can move freely in metals, water with dissolved materials. So your tap water has lots of salt in it. It can conduct electricity. And then materials that don't conduct electricity are called insulators. Okay? And the electrons can't move. Glass, plastic, and cloth. Okay? Now, if you have a high enough voltage, then sometimes there can be a breakdown and they will conduct electricity. So if there's very high voltage, when we were making our Tesla coil, okay, it didn't work, but we're going to get it to work next time. I know what's wrong. If you've never seen a video of a Tesla coil, you should watch one. And if we get it working, I want to bring it to class and show everyone. But we had a very high voltage in part of it, and I think that there was an arc. And so sometimes the insulation around the wire would actually start breaking down, and then we could see electrical arc. So we'd see little, it looked like miniature lightning traveling between the wires, which is not good. But at least we were getting a feel on the secondary coil. But I have a plan. You guys, you're in the physics club. And Joel, where are you? Where do you see? Oh, there's Joel. There's Joel. So if you want to come to the physics club meeting, we meet at Wednesday at 9. We're building a Tesla coil. It's really awesome. So you can come. It's in Shannon Hall if you want to. So pure water does not conduct electricity either. Now, another type of material that's extremely important for our modern life is the semiconductor. The semiconductor makes your American 21st century life possible, right? It gives us iPhones, it gives us computers. We can do all these amazing things with it. And it has really great properties. This is a replica of the first transistor, okay? So right here, this is the actual transistor. And this is big. It was probably like this big. So they took a piece of silicon here, and they basically attached 3 wires to it, okay? And what they did, and what's so revolutionary about semiconductors is by applying, if you hook up the wires correctly and you apply a voltage, it will change it from an insulator, to a conductor. Okay? And that's really a big deal because that now makes it possible for you to make computers. Okay? So, because now you can make a switch, right? So you can say, I'm going to leave this switch open and electricity is going to flow. Or I can close it and then electricity will stop flowing. So if it's closed, then the switch is closed and that's a 0. If the semiconductor is open, so if you've opened it, then that's a 1. Okay? So you can do 0s and 1s by turning on and off your semiconductor. And so now you can build, you can program a computer, so you can store data in it. Okay? So semiconductors allowed modern computers to be possible. Now, they actually had computers before semiconductors. The computers were made out of vacuum tubes. And if you've ever seen a picture of one of those computers, the first ones made out of vacuum tubes would fill up a whole room like this. Okay? They were very big, and you probably heard that expression, there's a bug in your program or something, or there's a bug in it. That actually came from one of the first computers, and the computer stopped working. And when one of these vacuum tubes would burn out, because they were kind of like light bulbs, okay, they had a filament in it and you had to run current through it. If one of them burned out, your computer would stop working. And so then you'd have to go check all 50,000 of these vacuum tubes and figure out which one burned out. And so somebody was programming one of these computers that stopped working, and so they started checking it, and one of them, a moth had crawled inside of it and shorted it out. So shorted 2 wires out. And so that's where the phrase, there's a bug in it, comes from, because there was literally actually an insect in it, and so the computer stopped working. Okay? So this was the first semiconductor in 1947, the first transistor. Okay, not the first semiconductor, they knew about that before that. The first transistor, sorry if I said that wrong, okay? And now we have a modern chip like this, okay? Think about the processor in your iPhone or your Android phone, right? We put literally millions of transistors onto something this big, okay? We've gotten to the point now where Intel can make transistors that are 23 nanometers across, okay? They can actually pattern things that small and make a computer out of it. And that's inside of your computer, that's how big the transistors actually are. So they're very, very small. And that's only been in, well, I guess it's 70 years now? Yeah, it's 70, right? 70 years since 1947. We've come a long ways since then. And probably in another 50 years, I can only imagine what computers will be like then. Probably they'll just put chips in your head, right? You can just close your eyes and surf the internet. Actually, you don't even have to close your eyes. You'll just see the computer screen in front of you, and you'll have Bluetooth in your head. So that's kind of scary, though. Don't worry about it. Huh? Well, that's not good. It's probably not good. Okay. So superconductors are materials that have no resistance. We did our little physics charade. Electrons can pass through a semiconductor without having collisions, and so there's no resistance. Actually, in modern power lines, when we make electricity at the power plant, by the very act of transporting it to here, you lose a lot of power just due to resistance. So a lot of the energy that we create is actually lost along the way because there's such big resistance. So if we could make our wires completely out of superconductors, we could save a lot of energy. Okay? So one type is niobium titanium alloy. It must be kept near the temperature of liquid helium, about 4.2 Kelvin. But actually a more common one is aluminum. So every pop bottle that you get is actually a superconductor. Aluminum becomes superconducting at less than 1.1 Kelvin. So you do come into contact with superconductors every day, but that's a very low temperature. The qubit in my refrigerator right now is made out of aluminum and aluminum oxide. So I have to get it below 1 Kelvin for it to turn on. Okay? So during the past 20 years, people have been trying to come up with high temperature superconductors. The goal, the grand vision would be to have something that's superconducting at room temperature, because then we could possibly make wires that have no resistance, and so that would be really great. Power companies would like that because they could save a lot of money, it would create less pollution, and it would be good. Okay. So that would be very useful if we had a room temperature superconductor. So right now the main application of superconductors is to make giant electromagnets. In my refrigerator, in my lab, I have a really big superconducting magnet. I have to use magnetic cooling to get down below 3 Kelvin. And it's a giant coil. You can't see it, it's totally encased in it, but I run 10 amps through the magnet, and I believe it creates a field on the order of a Tesla, which is a very big magnetic field, and that allows me to get my samples very cold. Okay. So circuits in quantum computers are also made out of superconductors. This is because we want no resistance inside of the quantum computer if possible. And we need it to be superconducting because we can harness some really cool quantum mechanical properties if we use superconducting materials. Okay? So magnetic resonance imaging, MRI, also relies on these superconducting magnets because you need to produce a very strong magnetic field. Particle accelerators. So at CERN, they have a very big particle accelerator at which they were looking for the Higgs boson with, right? And they think they found it, right? But when they first turned it on, they actually have to cool each of the magnets to 4 Kelvin. So they need a lot of liquid helium to do this, and so they have to cool the entire ring, and the ring is several kilometers in diameter, and so they use a lot of liquid helium. So now I worked at a smaller particle accelerator called the synchrotron, which is a very small one, but the power bill for that for 1 month was $100,000 for the electricity. So and the ring on that was, I don't know, the diameter was maybe 200 meters or something. And so if you have this giant super collider, then I can't even imagine what the electricity bill is for that. No, it's not the U.S. debt level. Okay, so these are Brookhaven National Lab. That's where I worked on their particle accelerator. It's called the synchrotron, the RHIC. Then the LHC at CERN near Geneva in Switzerland. So, and also in my adiabatic demagnetization refrigerator. Okay. So MRI stands for nuclear magnetic resonance imaging, and MRI produces very high quality images of living tissue. It's very important for medicine. So superconductors are very important. So the quality of an MRI image, signal to noise, is proportional to the magnitude of the magnetic field. So the bigger magnetic field you can produce, the higher resolution you can image things. Now, another thing you can do with magnetic fields, if you have a field big enough, say like 21 Teslas, you can actually levitate a frog. So living organisms are paramagnetic, and if you get a high enough magnetic field, the atoms in your body will actually try and repel incoming magnetic fields, and so it will actually cause a small animal like a frog or a mouse to levitate inside of the magnetic field. No, it was fine. Probably, I don't even think you would notice. Well, you might notice, but you don't feel like a horrific force gripping your body. Okay? So, for the most part, magnetic fields, when they pass through your body, they don't do anything. Okay, so they sell these bracelets at the store. Have you seen those? These magnets you can wear on your head that supposedly have healing properties? Doesn't do anything. Now, if you live under a high voltage power line where you have this this very high frequency oscillating magnetic field, that's different, because then you can have the oscillating magnetic field can actually cause problems in your body. It could actually knock off one of the electrons, and if that one of those electrons gets removed in your DNA, then that could maybe cause cancer. So, but for the most part, just a normal magnetic field has almost no effect on your body. Okay, so we can give an object charge. We can charge it up. Okay, so I can use my cat fur, and I can charge up this object here. Okay, not as human here today. So I can go like this. I hear a little bit of static electrical discharge, and I have now charged this up. Okay, so I have charged this object, and if I take this object and I connect it to ground, so I'm going to use my ground here, which is the sink, and I touch this part, then all of the charge goes away, and I have discharged my little electrostatic meter. Okay, so it's time to go, so I'll see you next time. And if you'd like to watch me pour out liquid nitrogen on the table, then come up here and I'll. It's really cool. Yeah. So maybe I will. No, there wasn't. So I'll bring my computer over here. Oh, wait. Then there's going to be... Okay, so if I pour the liquid nitrogen out on the table... So... So let me get a little container.
Cup is just
No, don't touch that.
Oh, that's cool, the wave on the top.
Okay, so hopefully you can see it a little bit better now. But so can you see it rolling around? Or?
Yeah.
Okay.
You can see it rolling off the edge.
Oh, here's the container. So if I put it inside here, so my ice is still in there. Okay, so it looks like it's... So we can see the little balls.
Ooh. Dude, it evaporates as soon as you touch it. I got this one.
Okay, so yeah, kind of trap it. And I'll put a little bit more liquid nitrogen in here.
Oh, that's... I don't know, dude. It keeps falling on my side.
It's like winter. Just dump the whole thing.
He just dumps out.
Dump the whole thing.
There we go.
Go for it.
Oh, yes. Put your hand in there, Corey.
So,
Bet.
Not scared of
anything.
think it might there you put your little tongue on.
I was like, put the computer.
No, I'm not gonna put my computer in it. No. Okay, so let's make a little thing in here and trap it.
Yeah, what would the balloon do? Pop?
Oh, it would just. Well,
Stick it in there. See what happens. Oh, just get like a coating on it.
It'll shrink. And get brittle.
It's still cool.
So cool. I broke a hole in it.
yeah, it cracked. Okay, so I'm gonna dump a little bit out here.
So much.
Now, if I let me put a little hot water in here.
Wow.
Okay, here, stand back.
He's so like chill with the laptop hanging out close to it. I'd be freaking out. It's so cool.
That's why it's boiling.
Yeah, it's
So I guess I don't know that's how
This
the
is so nice.
you had boiling water and then you drop dry ice.
Yeah.
It's like sticking your hand in a fridge, you know?
Shatter them off.
It's a bug that doesn't belong to any of us.
Yeah. What's his
well. I think.
Gonna get like on it.
Yeah.
So I guess we can. Well, I don't know if there's any liquid nitrogen left. Oh, there is.
Nah.
I have to quit. Actually, no.
So hold the balloon over it and see if it gets smaller.
Yep, sure does.
Oh.
Well, science.
It feels so nice.
But don't get your hand too close.
Burn your
So
fingers.
now take it out real fast and
Oh.
Is the bottom of it frozen? Oh. Hey.
This one. Is it hard or is it bad?
No, it's not.
It's just like normal one.
so it went back to normal. I don't have any food, otherwise we could freeze candy bars.
Oh my god.
You can also make ice cream out of liquid nitrogen.
Chemistry club did that actually.
Did they?
They were on Grand like handing out ice cream one time.
Oh,
That
that's
was
good.
last year though.
Oh, okay. Did they sell it to people?
No,
Or?
they were just handing it out.
Oh, okay.
That's how they're gonna do like John.
Oh.
Except like they never gave out information how to join.
Oh, so they didn't.
They were really bad at like joining process. process, but the ice cream process that was fun.
Me. Sign up.
So there's still a little.
That's not what I needed, my friend. Supposed to be happy.
On top of certain,
So our liquid nitrogen is boiling away, but you can still see it over in
That corner.
yeah, there's not very much left.
Well, it's not even a closed system. They're constantly pouring in liquid nitrogen.
Yeah, and since it's out in the air, right, the air is very hot. So just room temperature air in the container actually makes it boil. So if you look in here, see it's boiling a
I
lot.
say we need to get like
Like
some
a-
dish soap.
It's like a
Pour
pot
more
of
over the cup,
boiling
make a nice
water.
pot out of it.
So
You just like seeing that blend change.
Yeah. It's entertaining.
Oh, aren't you on the
Corey.
Aren't you on the We Play Frisbee football team?
Yeah.
Did you guys make it to
Yeah.
playoffs?
I don't think so.
Oh.
Literally killing this balloon. Dead.
It's
Freaking
so brutal.
Dead. Yep. It didn't break it all it should. Just inflate right back up. Where did it go? Magic. The bottom is still. It's hard as a rock. You need it up. Go away.
well, I guess that's all the liquid nitrogen I have. But yeah, so why did the volume decrease?
The gas. Gas on the inside.
Right, because as you there's PV equals nRT. So as you decrease the temperature, then the volume starts to decrease in the gas. So
Why does it heat it back up?
yes,
Bigger?
and as the air heats back up, then it inflates to its original size. So.
What do you think of this logo?
Oh, it looks cool. Yeah, I like it. See you guys later. Oh, you popped my balloon. All right.
Rough.
Yeah, that's good.
Yeah.
So you gonna join the SBS?
I think so.
Okay, that's good.
We have the. So is